Now we'll see Turing machines. Turing machines are basically they are an abstract view of a general purpose computer. That is, they tell you how a computer is present or the computations that are being performed, but they will not give you any idea on how these computations are performed. That is, you get an overview of the outside perspective, but you do not know what is actually happening inside. Now, these Turing machines were developed in the year 1890s. Around 1890s they were started, and the final draft was in the year 1936, and it was invented by a person named Alan Turing. These Turing machines, unlike normal deterministic finite automata and non-deterministic finite automata, they have stacks. Indeed, they have two stacks. These stacks are used to store, they provide memory to store your input, so that your input can not only be processed or just could be passed, but they can also be altered. Since this input can be altered, that is, input is modifiable, Turing machines also act as transducers. In general, they're acceptors just like your DFA and NFA. That is, they can check if a given string is acceptable or not. Apart from being acting as acceptors, they also behave as transducers. Now, they are a fundamental concept, and when you come to automata theory and theory of computations, they are mostly used in studying algorithms. To study algorithms like their complexity, and they also provide a way to model the behavior of algorithms and to analyze their computational complexity. Computational complexity as in the how much time it is taking and how much space it is consuming. Now, Turing machines can read input, they can write input, and they can also erase input. All this can be done on this long tape. We consider arbitrarily that this tape is of infinite length because you have two stacks, and it's possible to maintain infinite length because once you pop from one stack, you can automatically add it to another stack. So in that way, you can store your memory in one stack or the other. And to read input, it uses a set of rules. These rules are nothing but the transition functions. These transition functions are similar to the ones that are present in DFA and NFA, but they have additional writing symbols. That is, you change the input, right? So based on that, you'll find what the current state and the next state is. So coming to the mathematical definition of Turing machine, it is basically a 7-tuple machine. In this, as you know, Q is finite set of states, and then sigma is the alphabet, delta is transition, where if it is deterministic, one state will go to only the next state, and if it is non-deterministic, there are 2 power n in general. If you take this as n, 2 power n possibilities. And Q naught is the initial state, F is the final state, and then this here can also be written as this. It is read as tau. It is the tape alphabet. Now this tau is basically a representation for this infinite tape, and B is blank symbol. This blank symbol can be dollar or this delta or any other symbol that you can choose. It is basically used to represent a blank state. Initially, when you have an infinite tape, it's all blank. Then when you keep reading input, you keep rewriting that tape with the input symbol that you have, and sometimes you overwrite them with some other alphabets. Now this tau which you see the tape. The tape can basically have A, B are normal inputs, B blank, which is initially it's always present, and XY are the markers. These you use in order to mark a certain input. Now in Turing machine, after reading an input symbol, it will replace it with another symbol of the internal state. Suppose you have AB, AB. When it is reading, it could mark A with X or B with Y or whatever. And then after replacing it with another symbol, its internal state is changed and it reads from one cell to right or left side. This is how most of the transitions of Turing machine are present. That means when you encounter a symbol A, mark it as X, and then move to right. You'll understand this when you see examples. Don't worry about it now. Now, if the string is inserted in and if it is not in the language, then Turing machine will halt at non-final state. Now, these Turing machines are used to check recursively enumerable languages. Now, recursively enumerable languages are, type 0 languages. Recursive language, we'll first see what recursive language is. Recursive language. A language L is said to be recursive language if there exists a Turing machine which accepts all languages in L. Accepts all strings in L and rejects all strings that are not in L. Now, this recursive language, if the strings are not there, it will always reject, and if the strings are there, it will always accept. So it will basically always halt, and it will give you the result if the string is accepted or not. Whereas coming to recursively enumerable languages, when the string is present in the language, it accepts and the Turing machine halts. But when the string is not present, that is when it rejects the string, the Turing machine may or may not halt. Because sometimes in Turing machines there's no particularly defined final state. Such as if you take complement of 1 or complement of 0 as the question, that can be performed using Turing machine, but then you cannot give one final state because all you have to do is alter the input. You cannot say if it is accepted or not. Recursively enumerable languages are also known as partially decidable languages. And now we'll see some. There's also some theory about universal Turing machine and halting problem. We'll see these later after solving few examples.